All right, we are in lesson 2, recognizing quadratics through graphs. Last time we talked about recognizing quadratics through tables or data sets. Here we are going to now see what a linear function, an exponential function, and a quadratic function look like on a graph. So our goal is to be able to identify each of those by observing their graphs. Now we're going to go a little bit deeper than that. We're going to talk about the idea of domain and range and things like that. But before we do, go ahead and give this a shot just like you did last time. You're going to create a table, and then you can take that table and you have coordinates now, so you can plot those points on a graph and you can see what this looks like. So go ahead and pause the video, do what you can with it, and when you think you have an answer or you are completely stuck, go ahead and push play to see how you did. So in this case, when we create the XY chart, we can see in the first case, we have a total of, what is that? Looks like 7. And in the second case, we have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. In the third case, you can see that we're adding 1 to that middle line, and we're adding 1 on each end of the top and bottom. So we're actually adding 1 here, 2 here, and 2 here. So we're adding 5. So that should be 17. And we should go ahead and count the boxes to make sure. And then the next one, we should see 22. So the first thing we have to do is figure out what kind of function this is. So we're going to check our first differences. We're going to check our second differences, and we're going to check our multiplication. So first thing, let's check our first differences. That's the easiest one. You can see from 7 to 12, we're adding 5. And from 12 to 17, we're adding 5. And from 17 to 22, we are adding 5. And so we can see as a result of this, this is a linear function because the first differences are the same. All right, from here though, it says to go ahead and graph or plot those points in a graph. So I'm going to go ahead and do that here. It's going to be a pretty big graph because we have 22 as a height for the last one. So let's go ahead and let's see, go to 4. So we'll go ahead and just draw it out to there. All right. So this is our y-axis, this is our x-axis, and we'll go ahead and plot these points. And let me count how many I have here. I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So I don't have enough room to graph 22. So what I'm going to do is I'm going to cut the boxes in half or double the value. So I'm going to say that the first line is worth 2. And so it's going to increase by 2. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, and 22. That's as high as we need to go. In this direction, I'm going to skip every other one because I only have to go to 4. Let's see. 2, 3, 4. Yeah, we only have to go to 4. So we'll say that this is 1, 2, 3, and 4. And so this graph is not drawn to a scale that is proportional, but we can get an idea of what the graph is going to look like. Now, I really want to emphasize the importance of having graph paper when we are doing graphs and drawing as perfect as possible. Putting the points in the exact spot is so important. Now, granted, I know that we can't all draw perfect lines or draw perfect shapes. I get that. But we can use a ruler to draw straight lines, and we can plot points accurately. And that's so important when we're doing math. All right, in the first piece of data, we got 1, 7. So we're going to go over 1 and up 7. So we can see 6 and 8. So 7's right in the middle there. The next data point is 2, 12. So that's going to be right here. And then the next data point is 3, 17. So 17 is between 16 and 18. So that's going to be in the middle there. And the last data point is 4, 22. And so we have our 4 data points there. All right. Now, Create a table and plot those values on a graph based on the diagram below. So you can see it's linear because this follows a straight line pattern. Now yours might look a little bit different because you might have counted each box as 1, and so you would have gone a lot higher. And then actually, if you counted each box as 1 this way, it would be really steep looking. But as long as you have something that looks linear, that's okay. Now in these cases, these are called discrete functions because they're just data points. Because we don't have a step 1.5. We don't have a value in the middle of each of these. We can't have size 1.5 or size 1.25 necessarily. That wouldn't work for how many boxes are there. But if this was a continuous function, you can see that it follows a linear pattern. Again, normally we wouldn't connect these dots because it's discrete, but our focus isn't necessarily on discrete. Our focus is on the idea that it's linear, okay? And so we can see it's linear. And if we continue the pattern in both directions, well, the next one would be if we were to add 5 to this, we would go up to 27. So we go up to 5, we go up to 27. So that's 24, 26, 27's in the middle. So this would be our next point. And again, you can see it follows the same linear pattern. If we were to go backwards, so to get to the 0 size, then we would subtract 5. And so 7 minus 5 is 2. So at 0, we would hit 2. And so we'd have that point. Again, it's all in a straight line there, okay? But we're just going to graph the part of the function that's represented by the data here. All right, let's go ahead and take a look at the next one. Go ahead and do this one on your own. Pause the video and then come back and see how you did in the end. The question is how many triangles are in each data set. Okay, so hopefully you paused the video and you did this on your own. But for now, let's go ahead and do this. If I create the table, we can see that we have 1 triangle in the first one. In the second one, we're going to count all the triangles. So we can see we have 1, 2, 3, 4. 3 and 4 there. Okay, so we have 4. We're counting all the triangles. In the next one, we've got 1, 2, 3, 4, 5, 6, 7, 8, and 9. And then in the last one, we have 16, and I'll let you guys count that just to make sure. But from here, we're going to go ahead and create we're going to go ahead and check our first differences, our second differences, and our multiplication. In our first difference, we can see that we're adding 3. From 4 to 9, we're adding 5. And from 9 to 16, we are adding 7. And so we can check our second differences because we know it's not linear. So the difference between 3 and 5 is we added 2. And from 5 to 7, we added 2. So from here, we know that this is a quadratic function. Okay, this is a quadratic function. And so the purpose of this lesson is to kind of discover what a quadratic function looks like. We know it's not going to be a straight line because the pattern isn't linear. So what is a quadratic? What does that look like? Well, here is my graph over in the screen here. If I plot these points, I have 1, 1. So I'm going to plot that point there. We have 2, 4. So I'm going to plot that point there. Now, here it looks linear because when you connect 2 dots, you get a line between there. But here's where it's going to look a little bit different. Our next point is 3, 9. And so you can see that we don't necessarily have a straight line there. And the last one is 4, 16. Now, it's hard to tell. It's hard to see in this case. But if I were to try and connect the first dots with the last dot with a line, you could see that those other 2 points do not pass through that line, or that line doesn't pass through the other 2 points. So it's not linear here. Now I'm going to change the scale so we can maybe see this a little bit differently. And so instead of 1 being 1 here, 1 is going to be a little bit wider. So we got 1, 1, 2, 4, 3, 9, and then 4, 16. And so when we go to connect these, you can see a little bit more that it's not linear. So we don't have a linear function here. We can see that in the table anyways, but what does this look like? Oops. We can see that it's kind of got a curvature to it. right? And I'm not going to connect this. We will get more into this in the future. But you can see it goes up a little bit, and then it goes up more, and then it goes up more. So there's a curve to it. It's curving upwards. We would actually call that concave up. But that will be, concave up is a future math class. All right, let's go ahead and take a look at linear and quadratic functions. This is going to be notes for you for sure, so make sure you're taking good notes on this. Remember that linear, the graph of a linear function is a line. That's why it's called linear, okay? Its slope, or what we call the rate of change, never changes. It's got a constant slope. So every time you move over 1, you go up or down the same exact amount. It doesn't change. And so you get a constant line. In a quadratic, the graph is not a line. You saw it earlier. It's actually curvy. This curve is called a parabola. It's called a parabola. It's kind of a U-shaped thing, and you'll see more of that in a second. But the slope here in a quadratic is not the same. It's not constant. It does change. In fact, it changes constantly. In another functions that's true too, but this has a constant pattern to its change as well. So this is a complete parabola, a parabola that has parts in the negative x values and positive x values. So it looks totally different than a line. So if you see something that looks kind of U-shaped, that is a parabola, and the function is a quadratic function or a quadratic relationship. So that's the difference between a linear function and a quadratic function graphically. If you see a line, it's linear. If you see a U-shaped, it's a parabola or a quadratic. All right, so a parabola is the graph of a quadratic function. Again, this is notes, so take very good notes. If you need to pause the video to make sure you get everything down, go ahead and do that. But there are many places we see parabolas in real life. And this is kind of cool, and we can explore this a little bit, but I'll just give you some examples here, and I'll show you some pictures that go along with it. Something called projectile motion. So basically anything that you throw into the air or you kick into the air follows a parabolic path or a parabola. In architecture, we see it for design purposes, for just being aesthetically pleasing to the eye. For engineering, we see it for strength, for structures and bridges and things like that. And in different cases, you'll see more in just a second. Nature, we see parabolas all the time. That's kind of cool. We'll talk about that. And then in sports, we see it constantly because, like I said, it's projectile motion. Any ball traveling through the air follows a parabola. And the last one here is war, because when we're shooting cannonballs or firing bullets, those are going to follow a quadratic path. So here's an example of nature, a parabola in nature. You can see the U-shaped nature of the banana. You can see more nature here. Let me go ahead and get rid of this extra screen so you can see more of these. You can see that the fountain, the water fountain, follows a parabola. It goes up, the water goes up, and then it goes back down in a parabolic path. So that's kind of cool. In architecture or design, you can see a little bit of a parabola there. In engineering and architecture, again, you can see the parabolic shape of that arc. Roller coasters are going to be using those mathematical concepts of parabolas and even higher order functions like polynomial functions, trig functions that you get to later, but you can see the U shape going on there. I like this. This is underneath a bridge. You can see the parabola. The parabola is actually what's giving the strength to the bridge so that the water can be underneath it, and then cars or trains or buses or whatever it is can be on top of it and not collapse. So that's kind of cool there. This one I really like. This is a car light, a headlight, and you can use the same logic here with satellites or flashlights, and you'll see a picture of that in a second. But I wanted to share this with you because this is what's kind of cool about a flashlight or a car's light. If it's done mathematically sound, you get something that's kind of cool. Let's see if I can draw this more accurately so we have more of a perfect parabola here. So we have something, parabola looks like this. This is a sideways parabola. And if you look very closely to a well-engineered flashlight, you're going to see this kind of shape. You're maybe not going to see out here. You'll zoom in quite a bit, And so you might see, let's see, you might see, let me draw it a little bit as if it was zoomed in. You might see something like this on a parabola, okay? Now, with that said, the reason that a light bulb or a flashlight is shaped in the parabolic fashion that it is it's designed. Notice you have, in a flashlight, you'll have like this light bulb come out. Now, we know that light normally disperses evenly. So if this is my light bulb, normally light's going to shine out in all directions evenly, right? But if you notice, a flashlight condenses the light into one area. So it doesn't just shine everywhere. Car light's the same way. It shines forward, it shines out. And so the idea is that this whole parabola is reflective. It's going to reflect light. But the parabola is designed, or the function of a parabola is really unique in that when this light shines off of this central point, it's called the focus here, if it shines off of that and hits the parabola, it reflects in a manner so that it comes straight out. And then if I draw another light beam that maybe comes out here and hits the parabola, it reflects straight out. And then we do the same thing everywhere. A light beam here, it's going to reflect straight out. And then same thing here, as it comes out here, it's going to reflect straight out. And you can kind of see that a little bit. It's like playing pool. It reflects, it bounces off the wall in a manner that mathematically makes sense. And so no matter where that light shines onto the reflective surface of a parabola, if the light bulb is placed in the right place, in the perfect place, it's going to reflect off of the parabola, and all the light beams are going to go out in the same direction. And so you'll see this concentration of light on a wall or something like this, a circle of light. But you'll also see maybe a secondary ring that comes out here. Well, that's because the light that's coming out of the flashlight that's not reflecting off the parabola is going out in all different directions here. And so that's why you see a second, like a dimmer concentration of light. But the main focus of light is all coming from the reflections of the parabola. So you can see a real world application of parabolas. It's actually a really cool concept. And it's something that we just take for granted in our daily lives. When we grab a flashlight and we use it, some of us might go, I wonder how this works. Well, this is how it works. And so we're going to explore the idea of parabolas to help us understand those concepts in the future. All right, let's go ahead and take a look at some more cases. Here is a natural case, just gravity pulling a chain down forms a parabolic shape. Satellites, it's the same idea. The idea of a satellite is that information is actually coming into the satellite. So the information rays are coming in and hitting the parabolic shape, and because it's set up perfectly, they all bounce back to this central piece, and this is where all the data is collected. The information goes in, bounces off of the parabolic disc, and then into the receiver, and everything bounces perfectly into the focus. And so that's, to me, totally cool, and hopefully you appreciate that. Here's some engineering architecture. The strength of the bridge is from the shape of the parabola. Here's some sports, I guess you can say. Projectile motion, everything follows a parabolic path. What must go up? What goes up must come down. So that skier must come back down. Mark McGwire hitting a home run, that ball's going to go up and then go back down. Motocross or stunt stuff, you can see these parabolic shapes. Let me go back to that so you can see it a little bit. This shape of this parabola going up and going down every time. Shooting a basketball follows a parabolic path. Shooting a man out of a cannon follows a parabolic path. Okay, so there's lots of different examples of parabolas in nature and in science and in engineering, and it becomes beneficial for us as mathematicians to understand these things so we can help society along in that adventure. All right, so here's an example of this. This is an example, so I want you to write this down in your notes so you have a solid working thing that you can see and study as we go through this. All right, so I give you a table here. It says, using the given table, the table's off to the right. It says, identify the type of function and graph a continuous curve through the given points. Identify the domain and the range, find the average rate of change for 0 to 2 and 0 to 5. Now, I understand that you may not be familiar with this concept. That's why we're going to go over an example of this right now. Domain and range you should be kind of familiar with, but we're gonna see this throughout the year, and we'll define it a little bit more in the future and get plenty of practice with it. But let's go ahead and do step 1 here. And in step 1, it says identify the type of function. Well, we're going to check our first differences. So our first difference from 3 to 6 is up 3. From 6 to 7 is up 1. So we know right away it's not linear. From 7 to 6, it's down 1. From 6 to 3, it's down 3. And from 3 to negative 2 is down 5. So we know it's not linear. Let's go ahead and check our second differences. So what is the difference from 3 to 1? How do I get from plus 3 to plus 1? Well, I have to go down 2. How do I get from plus 1 to minus 1, or positive 1 to negative 1? I have to go down 2. From negative 1 to negative 3, I have to go down 2. And from negative 3 to negative 5, I have to go down 2. And so you can see, because the second differences are the same, this is a quadratic function. And if I go ahead and plot these points, you kind of saw it there a second ago, I'm going to go ahead and do this step by step to make sure you guys are good with this idea a little bit more. Now, we do have some negative regions here. So you're going to have like the example that's on the lesson and the example that is on the graph paper here, just so that we have, so maybe it helps you see it a little bit more, I don't know. All right, so we have our y-axis, our x-axis. Plotting the first point, we have 0, 3. So that's over 0 and up 3. The next point is 1, 6, 4, 5, 6. So that's this one. That's 6 there. That's 3. 2, 7. So that's just up 1 more there. So it's 1, 2, and then 3, 6. So it looks like we're coming back down. And then 4, 3. And then 5, negative 2. So it's actually down here. All right, so we can see this parabolic shape here. Now, I can't draw a perfect parabola, but I'm going to connect the dots the best way I can. And I find that by connecting with small little lines and picking up your pencil and going back and forth on it is going to actually make a smoother shape than just trying to consistently draw it dot to dot. So just little sketching, basically. So we can see this parabola taking shape here, and we can see that. That's pretty cool. So A is done. Identify the type of function. It's quadratic, and graph a continuous curve through the given point. So continuous, meaning that it's not discrete anymore. So we're gonna connect the dots in a smooth manner. Notice they're not straight lines from point to point. It's kind of curvy. For B, it says to identify the domain and the range. Okay, so I'm going to write down domain here. Now, there's two different ways to write down a domain and a range. There's the inequality notation, and then there's the interval notation. Remember, domain is the set of x values. So if I were to, let's say, draw a line at the x value where this graph starts. Now, we're only looking at the given data points here. So if I were to draw a vertical line at the first x value and draw a vertical line at the last x value, we can see the domain. The domain is from the green line to the green line. It's where the parabola starts, where the parabola ends. So in this case, we would say that it starts at 0 and then it ends at 5. Now we're going to use, this is going to be inequality notation, okay? So we're going to use inequality. So we're going to say less than x, less than 5. Now, notice that the table does have a value for x equals 0. So this domain does include 0. So we're going to put an equal sign there. And we have a value for 5, for x equals 5. So we're going to put an equal sign there. So this is inequality notation. The other way to write this is an interval notation. And the way we'd write that is 0, 5. And because we are including 0 with that equal sign, we're going to put a bracket around the 0. And because we're including the 5, we're going to put a bracket around the 5. So this is inequality form. This is interval notation. Inequality notation, interval notation. So that's the domain. And the range is the other direction. The range is the set of y values, So instead of drawing vertical lines where the x's begin and the y's begin, what we're going to do is we're going to draw horizontal lines that start at the lowest y value. Well, the lowest y value is this dot right here, so we're going to draw a horizontal line there. And what's the highest y value? Well, the highest y value is up here. And so you can see what we've ultimately done here is we kind of drew a box around our function. We have our domain that covers the vertical lines, okay, covers the boundaries from left to right, and then we have the range that covers our boundaries from from bottom to top. And so if we were going to write this down, the range is the set of y values, not x values, set of y values. And so because we're including those points, we would put less than or equal to on both sides. Now, what is the lowest point? The lowest point is the y value is -2. And the highest point, the y value is 7. And so the inequality notation for the range is -2 is less than or equal to y is less than or equal to 7. The other reason you can think of the fact that this has an equal sign to it is we could say, does the parabola actually hit the height of 7? Well, yes, it does. This point has a value of 7. So we put an equal sign there. Does the parabola actually hit the y value of -2? Yes, it does. You can see it in the data table as well. And so we put the equal sign there. And then for the interval notation, we would just say from -2 to 7, so -2 comma 7, and we're going to put brackets around that because it includes those two values. And we'll get to cases where we don't put brackets, and you'll see that. But that is B, that's our domain and our range. For C is asking for the average rate of change. Now, I want to write this down because this is important. Another way of saying average rate of change is just the slope. That's all it means. What's the slope? Okay? What is the slope between 2 points? Remember, to find slope, we use the letter m. It's y2 minus y1 over x2 minus x1. So we need coordinates in order to find this slope. Now notice let's see here, in the notation, it says find the average rate of change for 0 to 2 and 0 to 5. These are two different questions here. From 0 to 2, this is an interval. This is x values. And so what I'm going to do here is I'm going to create coordinates. The first coordinate is 0, comma something. And the second coordinate is 2, comma something. 0, comma something and 2, comma something. That is what this notation means here. 0, comma some value, some y value, and 2, comma some y value. So we can see that when x is 0, we can see that the y value is 3. So the first coordinate we're looking at is 0, comma 3, okay? And the second coordinate we're looking at is when x equals 2. So if I look at my table, when x equals 2, the y value is 7. And so we end up with those two coordinates. And the question basically is, what is the slope between those two coordinates there? So I'm going to go ahead and plug those values in. Well, what is y2? y2 is 7, y1 is 3, x2 is 2, and x1 is 0. So we're just plugging those values in. And then we simplify this. 7 minus 3 is 4, over 2 minus 0 is 2, and then we can reduce this to 2 over 1. So the slope for the interval 0, comma 2 is 2 over 1, or 2. Now what we can see in the graph is if we go to those coordinates, 0, comma 3, you can see this coordinate right here, 0, comma 3, and we see the other coordinate 2, comma 7, that's up here. The idea of the average rate of change, or the average slope, is just to figure out the slope between those 2 points. And so I'm going to draw a graph or draw a line that passes through those 2 points. And so you can see what slope? Slope is rise over run, so it's up 1, 2, 3, 4. That's where we got the 4 from. And then it's over 2, 1, 2. So that's where we got the 2 from. So our slope is 2, 1 for the first interval. For the second interval that it's given us, it says 0 to 5. So let's go ahead and give that a try here. From 0 to 5, well, the coordinate for 0 is still 0, 3. That's according to the data here. And the coordinate for 5, coordinate for 5 is 5, negative 2. And so we'll find the slope between those two points. So y2 is negative 2, minus y1 is 3, over x2 is 5, minus x1 is 0. So y2, y1, x2, x1. Negative 2 minus 3 is negative 5. 5 minus 0 is 5. So negative 5 over 5 is 1, or we could say 1 over 1. Okay? And then we can check that in our graph. Looking at those two coordinates, 0, 3 is again right here, and then 5, negative 2 is right here. So if I were to draw a line between those 2 points, I should see a slope. Oops, I did the math wrong on that. I should see a slope of negative 1 because negative 5 over 5 is negative. And we can see exactly that. If we count the slope, we're going down 1, 2, 3, 4, 5. That's where the down 5 comes from, negative 5. And then right 1, 2, 3, 4, 5, positive 5. So we get a slope of negative 1. All right, that is the example problem, and that is the big cue for today. Can you identify what type of function it is based on the table, the data? It's quadratic. Can you plot those points and recognize it as whatever function it is? It is a parabola because it's got that U shape to it. And then identifying the domain and the range through inequality and interval notation. And then finding an average rate. Now, again, the average rate, we're going to do a lot of practice with that. The domain and range, we're going to do a lot of practice with that. So don't stress out on that if you don't fully get it right now. If you have any questions, make sure you are asking me, though. Okay? Let's go ahead and go on to the last slide here. This is a practice problem, so you're going to go ahead and pause the video and do this on your own, and then come back when you're done to see how you did. We have a given table, and we want to identify the type of function, and then graph a continuous curve through the given points, identify the domain and range, and find the average rate of change for those 2 intervals. All right, we have 2 problems here. So go ahead and pause the video, see what you come up with, and then come back and see how you did. For number 3, let's find my bearing here. For number 3, we have a set of data from, let's see what we have here, negative 3, 4, negative 2, 0, negative 1, negative 2, 0, negative 2, 1, 0, 2, 4, and 3, 10. All right, you can see actually in this right away that it's kind of got a funky relationship going on here. We're starting in the positive realm, we're going to the negative realm, we're going back to the positive realm. So this is actually, can't be linear because you can't go down and then back up again. The only function that we are aware of that goes down and then back up is a quadratic. So let's check that. The first difference here is negative 4, then negative 2, then 0, then positive 2, then positive 4, then positive 6. Okay, so that's the first difference. No consistency there. They're not the same. So let's check our second difference. From negative 4 to negative 2 is up 2. Then from negative 2 to 0 is up 2. From 0 to positive 2 is up 2. From 2 to 4 is up 2. And from 4 to 6 is up 2. So we can see because the second differences are the same, this is going to be a quadratic function. Okay, so that's part A. And then it says plot the points on a continuous curve. So let's go ahead and do that. We are going to have, let's see, this isn't too bad, so we can go ahead and plot some points pretty easily here. Trying to draw, like I said, accurate graphs are so important in math. I don't want to see your parabolas looking like V's. They should have some curves to them. So let's plot those points. Negative 3, comma 4, negative 2, comma 0, negative 1, comma negative 2, 0, oops, negative 1, comma negative 2, 0, comma negative 2, so I had that one, and then 1, comma 0, and then 2, comma 4, and then 3, comma 10, so 4, 5, 6, oops, a little bit off of my drawn graph there, but you get the idea. And so again, drawing, kind of sketching this shape here, you can see this parabola. Now notice here, these are the same heights. They're not just going to be connected with a straight line. So this actually isn't the lowest point, but it actually dips below there somehow, and then it comes back up. So that's going to affect our domain and range. And at this point, we can't know exactly what it is, but we can kind of give it a guess. So if you were struggling with that idea a minute ago, we'll talk about that. We'll just give it the best guess we can. All right, so there's the graph of that parabola. Now it says to identify the domain and the range. So the domain, well, let's go ahead and draw our regions. So we start out, what is the leftmost? We draw a line at the leftmost point. We draw a line at the rightmost point. Our job is to kind of create a box around this. And in fact, I'm just going to go ahead and draw the box in its entirety. So the green lines are side to side, if you would, from the left to the right, or a left-hand line and a right-hand line. And then the pink lines that I'm drawing here are the low and the high. And so because we drew a box around it, we can see the domain and the range easily. The domain is left to right. So how far to the left do we go? Well, we went to negative 3 to x. To how far to the right did we go? We went to 3. So from negative 3 to 3, that's where this box is at. We're going to put less than signs here, and because these points exist, we're going to put the equal signs. If you're going to write interval notation, it would be a bracket, negative 3, comma 3. So that's our domain. For our range, that is from low to high. So what's the lowest point? Well, this gets kind of weird because the lowest point is below that negative 2. I don't think it gets down to negative 3. So I'm just going to kind of give it a guess right now. We're going to say negative 2.3. If you put something within the negative 2 range, that's okay. Less than or equal to y, less than or equal to, well, what's the highest point? The highest point was that point right there, which was 10. Now that's if we stop the parabola within this data set. If this kept going, our range is going to be different and our domain is going to be different. We'll talk about that more in the future. But in interval notation, it would be negative 2.3, comma 10, and then we put brackets around that. So that's our domain and our range. For the last part, it says to find the average rate, or remember the slope, over these intervals. So since I'm looking for the slope from negative 1 to 1, the first thing I have to do is identify the coordinates for those two things. The first coordinate would have been negative 1, comma, well, if I look at my data, negative 1, comma, negative 2. That's my first coordinate. And my next coordinate is 1, comma, 1, comma, 0. Okay, so that's my second coordinate. So we're going to go ahead and find the slope between those. Remember the slope. The slope is, let me pull this up so we can see it. The slope is y2 minus y1 over x2 minus x1. So we're going to get 0 minus 2 over 1 minus negative 1. Okay, so 0 minus 2 is negative 2. 1 minus negative 1. Well, minus a negative, you do the keep change thing if you would. So 1 minus negative 1 is 1 plus 1, which is 2. So our slope is negative 1 for that interval. Okay, and then for our other interval, which is from 1 to 3, identifying those coordinates. Well, the first coordinate is 1, comma 0. because again, 1 comma 0. Okay. Our next coordinate is 3 comma 10. 3 comma 10. And so finding the slope there, that's going to be 10 minus 0 over 3 minus 1, which is 10 over 3. And that can't be reduced anymore, so we'll say that's it. All right, so that is number 3 there in its entirety. You got the parabola. It's a quadratic because the second differences are the same. The domain is the furthest left to the furthest right. The range is from the lowest point to the highest point. And then the slopes, the average rate over these intervals, is the first thing we have to do is identify the coordinates and then plug into the slope formula. All right, for the next one, number 4, we have the data x, y. I'm realizing that this lesson is going a little bit long. This is going to be the last thing we're going to do here. 1, 2, and 3. So negative 15, negative 10, negative 5, 0, 5, 10, and 15. All right, so check our first differences. In this case, we went up 5. Oh, we went up 5 again. We went up 5 again. We went up 5 again, and up 5 again, and up 5 again. So we can see, because the first differences are the same, that this is a linear function. And this is a pretty big graph. So what we're going to do is we're going to count by, twos here to make sure that we get everything within our screen. All right, it's a little bit off here. So x and y. All right, so for negative 3, I'm going to go back 3. 1, 2, 3, that's negative 3, but I'm going to go down by 2. So it's 2, negative 2, negative 4, negative 6, negative 8, negative 10, negative 12, negative 14, negative 16. So negative 3, negative 15 is going to be right in the middle there. Negative 2, negative 10 is right here. Negative 1, negative 5 is right there. 0, 0, 1, 5, 2, let's see, 2, 4, 6, so 1, 5. 2, 10, let's see, 8 and 10. And 3, 15, 12, 14, and 16. So 15 is going to be in the middle. And so we can see our linear pattern there. See our linear pattern. Connect the dots with a nice straight line. There's that. Our domain for this guy, domain, and our range are going to be based on drawing a box around the figure. So if I were to draw a box that encompasses that whole figure, I'm going to draw this vertical line starting at the left, and I'm going to draw this vertical line that ends the box on the right. And then we're going to draw the horizontal lines at the lowest point and the highest point. And so we would say that the domain is from negative 3, less than or equal to x, less than or equal to 3. And then interval notation would be negative 3, comma 3. For range, the lowest point is down here. That was negative 15, less than or equal to y, less than or equal to the highest point, which is 15. The interval notation will be negative 15 to 15. There we go there. Again, if you're not fully getting domain and range or the average rate at this point, don't stress too much. We'll get plenty of practice there. The main point of these lessons is the table and the graphs. All right, for C, the interval from negative 1 to 1, if we look at that data, negative 1 comma negative 5 is the first point. And the next point is 1 comma 5. So we'll find the slope between there. So that would be 5 minus negative 5 over 1 minus negative 1. And it might be a good idea to put parentheses around what you're plugging in so you don't get mixed up with your minuses and your negatives. So 5 minus negative 5 is actually 5 plus 5, so that's 10. 1 minus negative 1 is 1 plus 1, which is 2. And so our slope is 5. Now, we kind of knew that, or 5 over 1. We kind of knew that because this is linear, the first difference is your slope. And because it's linear, the slopes are going to be the same no matter what points you pick. And let's go ahead and verify that. If I look at the next interval was from 1 to 3. Well, the coordinates for 1 was 5, and the coordinate for 3 was 15. So plugging into the slope formula, you get 15 minus 5 over 3 minus 1, which is 10 over 2, which is also, again, 5. So we get the same slope in these cases, and you always will if it's a linear function. All right, that wraps up this lesson. I know it was kind of a long one, but I don't think it was incredibly difficult. We were just looking for patterns in the table and recognizing that a linear function makes a line for a graph, and that a quadratic function makes a U-shaped kind of thing for a graph. And we saw some really cool applications of this in real life. So go ahead and do the assignment that's associated with these notes. If you have any questions, feel free to get a hold of me. Otherwise, have a great day.